Hi students, how are you? Hope you are all fine in this pandemic situation at your own places. Today I would like to deliver a lecture on Joule-Thomson effect, some equations derived from Joule-Thomson effect, and second and third law of chemical thermodynamics. So be ready to catch the lecture properly. As Joule-Thomson effect is an important part of chemical thermodynamics, so you all have to know the term, system, surroundings, thermodynamic process, and state functions. We surely know that thermodynamic system is that vessel or container where the overall thermodynamic process acts. So there are various types of thermodynamic systems such as adiabatic system, closed system, open system, and isolated system. Thermodynamic process. Thermodynamic process is the way of acting the thermodynamic treatment in the system. These processes are of two types. One is reversible process and another is irreversible process. The process which shows reversibility at all of its steps is called reversible process, and the process which is irreversible in nature is called irreversible process. Now I am going to the term Joule-Thomson effect. So what is Joule-Thomson effect? Joule-Thomson effect actually expresses the relation between the temperature and pressure of any adiabatic system. For any adiabatic system, this is the input pressure chamber and this is the output pressure chamber. When we compressed the system expands by its volume, and with the expanding of volume the temperature falls. And by observing the statement of Joule-Thomson effect, it states the phenomena of producing lowering of temperature when a gas is made to expand adiabatically from a region of high pressure into a region of low pressure. It's known as Joule-Thomson effect or Joule-Kelvin effect. If we go to the equation, we get W is equal to P2V2 minus P1V1. And if we look at the total entropy, we get del E is equal to Q minus W. But the process is adiabatic and therefore Q is equal to 0. So by putting the value of Q in the equation of entropy, we get del E is equal to minus W. That is E2 minus E1 is equal to minus W is equal to minus P2V2 minus P1V1. By rearranging, E2 plus P2V2 is equal to E1 plus P1V1, and this E2 plus P2V2 is equal to H2 and E1 plus P1V1 is equal to H1. That is H2 is equal to H1 or del H is equal to 0. Thus the Joule-Thomson experiment takes place at constant enthalpy. So we get the equation that the H2 is equal to H1. That means Joule-Thomson experiment takes place at constant enthalpy. So what is Joule-Thomson coefficient? Joule-Thomson coefficient is expressed as mu. The number of degrees temperature change produced per atmosphere drop in pressure under constant enthalpy conditions on passing a gas through the porous plug is called Joule-Thomson coefficient. Now come to the adiabatic expansion of an ideal gas. A process carried in a vessel whose walls are perfectly insulated so that no heat can pass through them is called adiabatic system. According to the first law, del E is equal to Q minus W. And as the system is adiabatic, so Q is equal to 0. That is, del E is equal to minus W. Since the work is done at the expense of internal energy, the internal energy decreases and the temperature falls. Considering for 1 mole of ideal gas, we know dE is equal to minus PdV. At constant volume, dE is equal to CV dt. Here CV is for molar heat capacity. So CV dt is equal to minus PdV. We know PV is equal to RT for 1 mole of ideal gas, or P is equal to RT by V. So CV dt is equal to minus RT dV by V, or CV dt by T is equal to minus R dV by V. Integrating both sides, considering CV is constant, then we get CV integration of 1 by T dt is equal to minus R integration of 1 by V dV, and the integration is running at the limit of T1 to T2 and V1 to V2. Thus, CV ln T2 by T1 is equal to minus R ln V2 by V1 after doing the integration. Since R is equal to Cp minus Cv, the equation may be written as ln T2 by T1 is equal to minus Cp minus Cv by Cv ln V2 by V1. But we know the ratio of Cp to Cv is often written as gamma. That is, gamma is equal to Cp by Cv. And thus the equation becomes ln T2 by T1 is equal to minus gamma minus 1 ln V2 by V1. By replacing negative sign, by inverting V2 by V1 to V1 by V2 and taking algorithms, we get T2 by T1 is equal to V1 by V2 to the power gamma minus 1. That is, T2 V2 to the power gamma minus 1 is equal to T1 V1 gamma minus 1 by cross multiplication. That is, TV gamma minus 1 is equal to a constant. From ideal gas relationship, we know T2 by T1 is equal to P2 V2 by P1 V1 for 1 mole of gas. That is, we get P2 V2 by P1 V1 is equal to V1 by V2 to the power gamma minus 1, as T2 by T1 is equal to V1 by V2 to the power gamma minus 1 from getting this equation. So P2 by P1 is equal to V1 by V2 to the power gamma. That is, P1 V1 to the power gamma is equal to P2 V2 to the power gamma. That is, PV gamma is equal to K, that is a constant. Thus, we get two equations. One is TV gamma minus 1 is equal to a constant, and another is PV gamma is equal to a constant. And these two equations are derived from the adiabatic expansion of an ideal gas using Joule-Thomson effect. Now come to the second and third law of thermodynamics. The second law of thermodynamics states that whenever a spontaneous process takes place, it is accompanied with the increase of the total entropy of the universe. That is, the total entropy or total energy of the universe is equal to the total entropy of the system plus total entropy of the surroundings. And the third law of thermodynamics states that the entropy of a system approaches a constant value as the temperature approaches absolute zero. The entropy of a system at absolute zero is typically zero, and in all cases is determined only by the number of different ground states it has. And that's the overall discussion of Joule-Thomson effect, its some derived equations, and the adiabatic expansion of the ideal gases, and the second and third law of thermodynamics. Students, I hope you will understand the lecture properly that I discussed today. Please keep your study going and be very much careful by yourself in this situation. wishing that we will meet in the classroom very soon. Till then, Allah Hafiz.